That is what I have done over here. So, the first term had the incident field, the second term had no incident field, and we are interested in solving this problem now. Okay. What was, remember the overall objective? I want the field everywhere. To find the field everywhere, I need to know these terms over here. So, grad phi 1 and phi 1, right. I have assumed that G1 and grad G1 through some effort I have calculated. For now, we will leave it as it is. So, I need to solve these equations. Let us say I solve these equations. Once I solve these equations, how will I find the field everywhere? Does this tell me the field everywhere? Do these equations tell me the field everywhere? Where? Where is phi 1 of r and phi 2 of r at an arbitrary location? Is it there, or is it only on the boundary? It is only on the boundary. So, suppose we solve this equation, how will this help us? You see the catch? Let us say I solve it through some very good math, we solve it, then what? Is my objective achieved? My objective was to find the field everywhere. Go back to the volume integral that we had started with, the current distribution on the wire. What did we do there first? We first found the charge density rho, and then we substituted it back into something to find the field, the potential. So, your hint is, which of the theorems did we use to write down these two equations? We discussed two theorems. One was Huygens principle, the second was extinction theorem. These two equations are which ones? Extinction theorem. So, what have we not used? Huygens principle. We have not used it yet. We only wrote the extinction theorem. So, let us go back to the expression over here. I use the bottom two equations. I use this and this. So, now can you tell me, supposing I solve for and find phi 1 and grad phi 1, how will I find the fields everywhere? Use Huygens principle, right? Because once I evaluate this guy and this guy, I can use this theorem, which will tell me phi 2 everywhere. Similarly, phi 1 everywhere, right? So, always in the integral equations, there is a two-step process. First, evaluate an intermediate variable. In that case, it was charge density on the wire. In this case, it is phi 1 grad phi 1, phi 2 grad phi 2 on the boundary. Then I can substitute it back into Huygens principle and get the field everywhere. Okay. So, you should always have this high level picture in mind, that this is the strategy that we are following. Otherwise, it is easy to get lost in math, right? Clear? Alright. So, let us go back here. So, this was the extinction theorem, as I already mentioned. Now, let me ask you, how many variables are there in these two equations? What all do I not know? I do not know phi 1, okay. Anything else? Phi 2, anything else? I do not know grad phi 1 dot n hat and grad phi 2 dot n hat. So, you must be thinking that if I know phi 1, I can calculate grad phi 1, but that is actually not going to happen, because let us assume that there was no grad phi in these equations and only phi. We have seen that if I have an unknown variable inside an integral equation, we have seen one way of solving it, and what was that one way? Discretizing and solving. That gave you phi, alright, but it gave it to you in analytical form or numerical form? It just gave you a bunch of numbers. From that, how will you accurately get grad phi? You will not get, right. So, grad phi 1 dot n hat is actually your second variable. It looks like I can derive one from the other. That would be true if I were getting phi 1 as a function, then I can take its gradient, but I am not getting it as a function. So, there seem to be 4 variables and how many equations? 2 equations. So, some budgeting seems to be off, right. I can't solve for 4 variables from 2 equations, but what I have been saying so far is boundary conditions. I have not yet used the boundary conditions, right. So, what are the boundary conditions that we have studied in electromagnetics? Simple boundary conditions. Tangential E fields are conserved, tangential H fields are conserved as long as there are no pure surface currents. In this problem there are no pure surface currents because I did not say that it was a pure metallic object or something, it was some dielectric object, right, like like a piece of wood or whatever, right. So, I know that physically there are no surface currents. So, E tan is equal to E tan 1, let us write it. And the second equation, second boundary condition is these are the two boundary conditions. Yeah.
So we consider the scattered field is from the object volume V2.
Yeah.
Means it is not penetrating inside.
No, it is penetrating. Of course, it is penetrating. It is a dielectric object. It has some permittivity. So, the incident field will go inside the object. Some of it will get scattered by the surface. Some of it will go inside, and it will re-emerge. So, it is a fully complicated situation. So, it is not. If I had a perfect metallic object, then the field will only bounce off. That's a special case of this. Okay. If I make the conductivity part of this epsilon tending to infinity, I will get that relation that it will become a impenetrable object. But right now I am taking it to be a penetrable object.
It's a dielectric.
It's a dielectric. It has a real part and imaginary part. Okay. So let's take up the first of these equations. So I should draw this again over here. This is V2, V1, and this is my current source over here. So what was in the assumptions that I made, what polarization am I working with? TM polarization. What is the electric field in this case?
EZ.
Only Ez, right? So E is actually only Ez z hat, and the further notation that we made was we called it by the symbol phi. That was the variable that I was solving everywhere, right? So remember, this being a 2D problem, this object extends infinitely in the z dimension. Okay. So if I take one point over here and one point over here, and I move this point over here, and I move this point, I am trying to move as close as possible to the surface. As I move as far as possible, I mean as close as possible to the surface, I will be able to ask what the boundary condition is. So for E tan 1, what would be the boundary condition? On the boundary S, what can you say about the E tan 1 is equal to E tan 2? Which direction is the electric field? Only along Z. Is this constant this Z axis vector, is it tangent to this surface? Yes, right, because this object extends infinitely out of the plane of this paper or board. So the Z axis, any point, any line parallel to the Z axis is tangential to the surface. So what does this equation turn into?
Z equal to
Yeah, okay. Phi 1 of r prime is equal to phi 2 of r prime on S. Okay, and S is anyway the place where I am doing this integral. Okay. So now how many variables can I say? So these two have been condensed into, I can call it equal to some phi r prime, but only on S, okay, not anywhere else, right. So now from here I have combined, I have merged it into one variable. So it seems like now I have 3 variables, 2 equations. This part clear? Okay. So I mean you would have guessed it by now. The next equation is going to help me further reduce the number of variables. Okay. So let's look at it now. The second boundary condition is going to be H tan 1 is equal to H tan 2. Now this is going to be a little bit tricky. How do I get the magnetic field now? Before I get to tangential component of the magnetic field, I should first get an expression for the magnetic field and then take its normal or tangential component, right. So how do I get the tangential field? I mean, how do I get the magnetic field? Curl of E, right. So we have curl of E is equal to minus dB dt, which is minus j omega mu naught h. That is my Maxwell's equation, right. So, if I know E, can I get h, right. So, I can express h in terms of phi, right. So, let us just write this over, let us write this over here. I have x hat, y hat, z hat, right. What are the components of E? X component 0, 0, phi, right. And phi, remember, is going to be a function of r, which is a function of x y, not z, right. So, which component will be which component will survive over here? Let us look at the x hat component. So, x hat component will be dou phi by dou y, right. The y component will be
dou phi by dou x.
Are you sure?
Yes, sir.
Dou phi by
Dou x
minus, exactly, and the z component 0. Not surprising, I started with a vector in the z direction, curl of it gave me something in the xy plane, right. So, this is my right. So, from here I can say that what will h be? H will simply be j. So, let me get this out of here. So, it's j by omega mu naught, okay, and I have dou phi by dou y minus dou phi by dou x. So, I have got the magnetic field, that is step 1. Next, what do I need? I want to enforce tangential components. What do I know about the surface? What has been given to me in the surface? Normal vector, yeah. So, assume that I know the normal vector, okay. So, I can write down h as so sort of h tangential plus h normal. I can break up any vector in the plane in terms of a normal component and a tangential component. I can do that, okay. So, that tells me that the h tangential, which will be h t along the tangential direction, I can write that as h total minus h normal. How do I write out the normal component of the field? Just take the dot product of h along n, right. So, this can be written as h minus h dot n hat. So, this term over here is what I have to enforce on the boundary, right. So, it looks a little complicated, but all I have done is I have extracted the tangential field in terms of the magnetic field and the normal to the surface. Okay. So, let us try to calculate this now. Okay. So, let us see. So, what should we do? We can just substitute this over here. Okay. So, what will this be? So, let us further write down the normal vector as nx ny 0. Okay. So, we can keep this j by omega mu naught outside common. Okay. The first component over here. So, what will that be? So, let us take this term over here. This is simply going to give me d phi by dy. Okay. H dot n along n hat. Okay. So, let us write down h dot n first. So, h dot n is going to give me j by omega mu naught. What else? What is h dot n? Nx d phi by dy minus ny d phi by dx. It is the dot product of h, which is here, and n, which is here. So, the x component multiplies by the x, the y component multiplies by the y, and the 0 is 0. So, this is a scalar, right? This is my h dot n hat, and then I am taking this scalar and projecting it along the n direction, right? Everyone's with me so far? Okay. So, the same component here will get multiplied along nx and along ny, right. So, when I write down the nx part over here, the x component of the total h tan over here, what do I get? So, this is coming from h minus nx dou phi by dou y minus ny dou phi by dou x. This is the x component. Y component is going to give me dou phi with a minus sign by dou x, okay, and minus ny nx dou phi by dou y minus ny. Right. So, on expected lines I have got some vector with a x component or y component and no z component, right. That is what we expect. So, I have always been writing this as n hat, that means it is a unit vector. So, what does that tell me in any relation? Nx square plus ny square is equal to 1, okay. So, look at these two terms over here. Can they be combined somehow? It is 1 minus nx squared into something. So, that becomes ny squared. Okay. And what about the other term? Plus nx ny dou phi by dou, okay. What happens to the second term? Again this and this can be written as nx squared dou phi by dou x will come, okay, and I will get a, what will I get?
So, minus nx.
This will be minus, correct, and the nx ny term will be okay. Again still does not look very straightforward over here. Can I take something common from, looking at this, the first term has a ny in both the terms, the second term has a nx in both the terms, right. If I ask you what is grad phi dot n hat, okay, so grad phi dot n hat, what will you write? Let us write it over here, grad phi dot n hat. What will you write it as? Nx dou phi by dou x plus ny dou phi by dou y, right. Do I observe that term anywhere over here in this expression? It is there, right. It is ny times grad phi dot n hat. What else? Minus nx grad phi dot n hat 0. Final manipulation, what does this look like? There is something common which is grad phi dot n hat, grad phi dot n hat. Does this look like the dot product between, I mean, can I think of this as a, not a dot product, there is a tangent. So, if n is, exactly, if n is nx ny 0, what can I say is tangential field? Minus ny nx 0, that is the tangential field up to a sign, because look at the dot product of this. What is the dot product of this? 0, right. So, this is the tangential field. Now, having seen this guy over here and having seen this expression over here, can we further simplify this? Can we write this as grad phi dot n hat, a scalar, times ny minus nx 0, which is nothing but grad phi dot n hat along t hat. We were finding H tangential field. So, what I have got is H tan is, there is a j by omega mu naught grad phi dot n hat along t hat. Granted, we had to do some amount of work to get here, but patiently we only work, this is just working with vectors, cross product, dot product, so on. Okay, now finally now we can say, so given that this is the tangential field and it should be conserved at the boundary, what does this tell us? So it tells us that grad phi 1 dot n hat should be equal to grad phi 2 dot n hat on S, right. So all we did was, we wanted the magnetic field, we started with the Maxwell's equations, which allowed us to express H in terms of E. Okay. So I got an expression for H. When I got the expression for H, I found out I tried to get the expression that gave me H tangential. H tangential, I had to do a fair amount of algebra to write it in terms of grad phi and the tangential field, which is what I got over here. Okay. And I say that it should be equal, and that gave me this boundary condition. So the first time you see this kind of a derivation, it seems a little intimidating, but you get the hang of it. Rest of the stuff is just repeating this in, being clever about the boundary of the problem and just doing this manipulation. Okay. And notice that we kept the surface to be completely general. As long as you tell me n, I can do this, right, nothing very special. I did not need like a rectangular boundary or a circular boundary, it can be any boundary, right. So these are the final sets of equations that we have. Our unknowns are over here, grad phi dot n hat and phi, similarly here. So these are two equations, two variables. Okay. So what kind of an integral equation do you think this is? We have studied different types of integral equations. This is a slight variation. So does it look like a Fredholm or a Volterra? Fredholm, because the limits of integration are known. So it's what kind does it look like? First or second kind? The unknowns, are they inside and outside or only inside the integral sign?
Inside.
Only inside. So we can say first kind. But what is different about it is that I have two variables. So these are actually coupled system of equations. It's not one equation in one variable, it's two equations in two variables. So these are coupled set of Fredholm integral equations of the first kind, right. Many adjectives to describe two simple equations. Okay. How will we solve these? Actually, solving these equations, there's no great mystery over here. We already know it. What is the process? We've done this in the previous problem. So what would you first do? Any equation you want to solve it, what would you do? Discretize it, right? So we would do a discretization. Then what is the other important choice? Basis functions, right? I have to choose the basis functions. And solve the system of equations. Okay. The parts which we have not studied so far are what are these guys and what are these guys. Okay. So that will be another module on Green's functions, which we will come to. Okay. So how these equations were different from previous was because of the coupled nature, and also these are boundary integrals. Previously we had just volume we had chopped up into segments. Okay. So these are the final sets of equations. Solving this gives us grad phi dot n hat phi 1 substitute that back into Huygens principle, and I can get the field anywhere I want. Okay, that's the basic idea. Is this clear? Okay. So how do we go about we'll cover how we'll solve this in great detail. We will not need to decouple them. We can solve them as is. We will form a linear system of equations from here and solve it as Ax is equal to b. Okay, that's how we'll solve it. There's nothing very fancy involved in solving these equations. Like, you don't have to do some change of variables to some other domain where they become decoupled, all of that. All that is not needed. Just discretizing, choosing basis functions. Okay. There's a lot of work that will go into evaluating these terms. Okay, I'll give you just one hint what the challenge will be. Along this bound, so what is your variable of integration over here? Primed or unprimed? Unprimed, right? There will be points where r is equal to r prime, right? And when r is equal to r prime, go back to the definition of G1, what happens? There's a delta function sitting at r minus r prime. So there's a singularity there. So we have to do the evaluation of these integrals in the presence of a singularity. So some amount of careful work is needed over there. Then the rest is simple. Okay, but we'll get to it. We'll solve it in great detail. Okay.